In this lesson, we're looking at modeling using variation, and we're going to look at 4 types of variation. And you'll see that even if you haven't used this language before, that you've probably done a lot of this type of work in the past. So we'll start with a very basic example, this one about hair growth. Your hair grows approximately 1.2 centimeters per month if you don't cut it. How long has your hair grown in 8 months? Well, you could model the situation with this formula, H equals 1.2 M, where M represents the number of months and H represents the length of your hair. So if we wanted to talk about how much your hair has grown in 8 months, we could say that H equals 1.2 times 8, so that H equals 9.66 centimeters. Okay, so very basic formula to model hair growth. Okay, so what we can say about the length of the hair and the number of months, though, is that the length of hair varies directly as the number of months, and that 1.2, this 1.2 here, is the constant of variation. So it's the one number that stays in the formula as the number of months or the length that the hair has grown will vary with time. Okay, so if we were to graph this situation, the line would go through the origin. So it would start at 0, 0 and go up in a straight line. Okay, anytime that you've got direct variation, you end up with a graph that starts at 0, 0 and increases in a straight line. If we know that two variables vary directly with each other, we can use this to create a formula to model the situation and to answer problems. So here's an example. The volume of blood in your body varies directly with body weight. If a 160-pound person has 8 pints of blood, how much blood does a 220-pound person have? There is more than one way to correctly solve this type of question. Because we're working with variation, though, and we're going to be looking at some more complex methods of variation, I'm going to teach you a method that for some of you will go, oh, but I could do it a different way, which is great. But the steps that we're going to follow with this one are going to be the same steps that we'll follow with the other types of variation. So that's why for some of you, you might think that the way I'm doing it is kind of awkward, but it's because I'm modeling a method that will work for all types of variation. So, so we've got a 160-pound person has 8 pounds of blood. How much blood does a 220-pound person have? So we're saying the volume of blood varies directly with body weight. So K is always used as the constant of variation. So that was the 1.2 in the other situation. So we could model this where B represents the volume of blood equals K times W. Direct variation always has this type of formula. So we can say that so when we say the volume of blood varies directly with the body weight, that K is going to be multiplied by the body weight. So we can look at the example we have. We can say that 8 pints of blood goes with a 160-pound person. So we can now solve for K by dividing both sides by 160. And we'll see that K is 1 over 20. So there's our constant of variation. So our formula then becomes B equals 1/20th W. So now we can answer the question, which is how much blood does a 220-pound person have? We've been given the 220 pounds, so the volume of blood is 1/20th of 220, so B equals 11 pints of blood. So if a situation is described by an equation in the form y equals kx, where k is a non-zero constant, we say that y varies directly as x, and k is called the constant of variation. Okay, so we're very careful with the language. We say y varies directly as x if we can write it as y equals some constant times x. And so these are the steps that we'll use, and we'll, as I mentioned earlier, we'll repeat those steps for every type of variation that we're doing. So write an equation to model the situation, substitute the values that you've been given, and solve for k, substitute k into your formula, and then use that formula to solve whatever your question is. So let's move on to an example. This one comes from your textbook. The number of gallons of water, W, used when taking a shower varies directly as the time, T, in minutes in the shower. A shower lasting 5 minutes uses 30 gallons of water. How much water is used in a shower lasting 11 minutes? So we can model this question by saying the amount of water varies directly with the time that it takes. So W equals KT. So we just set up a direct variation formula. Plug in the values. We know that a 30 gallons is used in 5 minutes. So we can see that K, our constant of variation, is equal to 6. Let me just fix that up a little bit there. So K equals 6. So now we substitute that into our formula. So W equals 6T is now our formula. And so an 11-minute shower will be 6 times 11, and the amount of water used will be 66 gallons. Okay, so the math itself is not difficult. The steps are will come more smoothly with a little bit of practice. Direct variation can also occur with powers. So in this case, we would say that y varies directly as the nth power of x. So in this next example, the distance d that a body falls from rest varies directly as the square of the time of the fall. If a skydiver falls 64 feet in 2 seconds, how far will they fall in 5 seconds? Okay, so the distance varies directly as the square of the time could be represented as d. The distance equals k, our constant that we're going to solve for, of the time squared. So in the example that we have, the distance is 64 feet in 2 seconds. Okay, so 2 squared is 4. We'll divide both sides by 4, so we'll get k equals 16. We'll substitute that into our formula now so that our distance equals 16t squared. So our distance now is 16. We want to find out how far they'll fall in 5 seconds. So it's 16 times 5 squared, 16 times 25. So our distance will be 400 feet. And hopefully shortly after that they open up their parachute. Another example. Again, this one's from your textbook. The weight of a great white shark varies directly as the cube of its length. A great white shark caught off Catalina Island, California, was 15 feet long and weighed 2,025 pounds. So what was the weight of the 25-foot-long shark in the novel Jaws? So we can say the weight varies directly as the cube of its length. So W equals k times the length cubed. So the weight that we were given was 2025 equals k times 15 cubed. Let's pull out our calculator, solve for k, and we'll get 0.6. So we'll substitute that into our formula, and W equals 0.6 times. Now we want to put in the length of the new shark to find its weight. It's 25 feet long. 25 cubed. So again, pull out your calculator, and 9,375 pounds, or almost 5 tons. And that's direct variation. So that's the first type of variation that we're looking at. And then the second one is called inverse variation. So when two quantities vary inversely, when one quantity increases, the other one decreases. So you can see that the formula looks a little bit different. It becomes y equals k divided by x, or you could think of it as k times 1 over x. And again, k will be a non-zero constant of variation. So here's an example to demonstrate how that might work. Kentville and Yarmouth are 227 kilometers apart. The time it takes to travel varies inversely as the speed at which you drive. I apologize for these typos here. Speed at which you drive. So if the average speed that you drive to go from Kentville to Yarmouth is 50 kilometers per hour, your time will be 227 kilometers divided by 50 kilometers per hour, and it'll give you 4.54 hours. However, if your average speed increases, okay, your time will be 227 over 100, which is only 2.27 hours. Okay, so as the speed increases, the time it takes to travel the distance decreases. That's an example of inverse variation. If your k and x are values greater than 0, an inverse variation graph will look like this. So as your speed increases, your time will decrease. Here's another example. The pressure P of gas in a container varies inversely as the volume of the container. So the pressure of a gas sample in a container with a volume of 16 cubic centimeters is 24 pascals. If the sample expands to a volume of 22 cubic centimeters, what is the new pressure? So the more space you give the same amount of gas, the pressure of that gas decreases. So let's model that. So we're talking about pressure varying inversely as volume. So we can say that P equals K over the volume. And in the example we have, the pressure is 24 when the volume is 16. And we can solve for K to get 384. So P equals 384 over V is our new formula, and this formula will now work for all sorts of volumes and all sorts of pressures of the same sample of gas, okay, and could be used repeatedly. But now we're looking at what's the pressure if we increase to 22 cubic centimeters. So P will be 384 divided by 22, so the pressure will be 17.5 pascals. Let me just fix that 17 there. Okay, let's look at another example. And again, feel free to press pause and work out the example on your own and then check it. The length of a violin string varies inversely as the frequency of its vibrations. A string 8 inches long vibrates at a frequency of 640 cycles per second. What's the frequency of a 10-inch string? So the length varies inversely with the frequency. So length, L for length, and F for frequency. So the length of 8 inches gives us a frequency of 640. So if we multiply there, we'll get K equals 5120. So there's our formula, 5120 over frequency. So if we have 10 for our length, our frequency will be, oops, We'll multiply both sides by f, divide both sides by 10, and we'll get a frequency of 512 cycles per second. Okay, so that's inverse variation. It's k divided by the other variable instead of k times the other variable. Combined variation is where you have direct and indirect variation occurring at the same time, because in real life we need slightly more complex models for what goes on sometimes, so that we could have these things happening at the same time. So for instance, we could have a situation where monthly sales vary inversely as the price of the product. So that makes sense. As the price of the product goes up, the monthly sales go down. Inversely as the, oh, sorry, I'm doing the second one first here. So if they vary inversely as the price of the product, you can see that sales could equal K divided by the price. In the first one, monthly sales vary directly as the advertising budget. So as the advertising budget goes up, the sales also go up. That could be modeled with sales equals K times the advertising budget. So we could put those two things together to get a new formula that would say that sales equals Ka divided by P. So there could be some constant that we multiply by A and then divide it by P, the price, to get our monthly sales. So here's an example. When $60,000 is spent on advertising and the price is $40, monthly sales are 12,000 units. So let's put that into our formula. So we'll have 12,000 equals K times 60,000 is our advertising, divide by 40, and we're solving for K, remember, is our first step, so we get K equals 8. So now we can say that sales equals 8 times our advertisement divided by the price of our product. So there's our formula that we can use. What are the monthly sales if advertising is increased to $70,000? So we can use our formula. S equals 8 times 70,000 divided by 40. The price has stayed the same, and we can see that sales will increase to 14,000 units. Okay. Here's one example. I don't want you to take it to heart too strongly. The number of minutes needed to do a math assignment varies directly as the number of problems and inversely as the number of people working on the problems. It takes 4 people 32 minutes to solve 40 problems. How many minutes will it take 80 people to solve 64 problems? So we're talking about time. Okay, the number of minutes needed to do a math assignment varies directly as the number of problems. So let's say that the time varies directly as the number of math problems. We'll use math for that, M for math, and inversely as the number of people. So M is number of problems, and P is number of people. Okay? So we're varying directly as the number of problems, inversely as the number of people working on them. So in our first, what we've been given is that it takes 32 minutes to solve 40 problems by 4 people. So K, if we solve that, we end up with K equals 3.2. That's our, 3.2 is our constant of variation. So now we can say that the length of time will take 3.2 times the number of problems divided by the number of people. So now we have the question, how many minutes will it take 8 people to solve 64 problems? So T will be 3.2 times 64 divided by 8, and our time will be 25.6 minutes. And our fourth and final type of variation. So far we've done direct variation, inverse variation, and then joint, which combines the direct and inverse. Combined, and now we're doing joint variation, which occurs when a variable varies directly as the product of two or more variables. So we can say in this example, y varies jointly as x and z. Okay, so instead of just y equals k times x, we've got y equals k times x times z. And here's an example. Isaac Newton's formula for gravitation is that the force of gravitation between two bodies varies jointly as the product of their masses. So there's the product of their masses in the numerator. That's that joint variation piece. And inversely as the square of the distance between them. So there's a piece of inverse variation because we're dividing. G is the gravitational constant. So the G is like our K, our constant of variation. Okay? So that's an example of joint variation that's actually used. Perhaps our physics students could confirm this for us. Question 10, which is again from the textbook. The volume of a cone V varies jointly as its height and the square of its radius. A cone with a radius measuring 6 feet and a height of 10 feet has a volume of 120 pi cubic feet. So let's look at just that first sentence. The volume of a cone varies jointly as its height and the square of its radius. So the volume varies jointly, so it'll be K times it as its height and the square of its radius. So V equals our constant of variation times height times the radius squared. So now we're given all of the details about one cone. So it has a volume of 120 pi. And its height is 10 feet. And its radius is 6 feet. Okay, so 120 pi equals 36 times 10 is 363, 6 to K. So K is equal to 120 pi divided by 360, or 1/3 pi. Or you could write that as pi over 3. Okay, and we're leaving that pi in there for precision purposes rather than doing any sort of rounding. So now we can say that the volume is pi over 3 times the height times the radius squared. So now we have a formula for volume of a cone. I keep wanting to say coin. So the volume will be pi over 3. For the question, we've got the volume of the cone having a radius of 12 feet and a height of 2 feet. So it'll be pi over 3 times the height of 2 times the radius squared. So our volume will be pi over 3 times 12 squared is 144, times 2 is 288, divided by 3 gives us 96 pi cubic feet, because our measurements are all in feet here. Or you could think of it as feet cubed. And that's it for the 4 types of variation.